If you want to, let me know. I can do
Sorry, I don't have to say.
Okay.
Oh, did you know what it is?
No, I want you to staple it,
Oh, okay.
but I want you to staple it.
Oh, then. Then let me put my name on the other two pages here.
No, it's okay.
Okay.
I'm not going to disentangle them. I'll staple them all later, I guess. Okay, anyone else have homework?
Use it on, what's called slave, or the.
Is that okay? You can see your kids again?
Wrong guard, so yeah, it's gonna be way above stuff like that.
How's everyone doing? How's your weekend? Great.
A lot of heat enough.
A lot of you now. I mean, I hope you're not lying. Okay, here's the first question I have for everyone, and I want folks to do this without looking at one another. So everyone closes their eyes after you read these possible options. The options are yes before every class, yes, but after class, sometimes when I'm doing homework, not really, and never, don't even own it. And this is in reference to how often do you read from the book? So what I'm going to ask you to do is close your eyes and then show me with your hand where option 1 is the first one and option 5 is the last one. You can do one, I'll give you a half with your other fist. But now I know your answer, so close your eyes. So I don't want people to feel like they're pressured. I want to get a real sense for how much people are using the book. So close your eyes. All right, and then show me with your fingers. Okay, hold them there. Missing one. Okay. Good. All right, that's fine. So I'm glad no one said 5. No one even said 4. So that's good. So you find the book somewhat useful? Anyone hate the book? Well, then you haven't really studied enough yet. I hate this book so much. I hated it as an undergrad, and I hated it more in grad school. But you eventually will learn to love it. We are going to be doing basically the end of electrostatics and matter today, if I can get this right. And we're going to do sort of like a broad perspective as we transition to magnetostatics and matter. And then we'll do how do these two weird unrelated phenomena fit into one another. And we're going to go into electromagnetic waves. My understanding is that you've already done things like conservation of energy in, right? Conservation, okay. So it would be like chapter 8, I believe, something like that. I'll touch base with you in 3 weeks when we finish magnetostatics and matter. So that's my goal. We have taken a very abstract concept like charge, which folks don't really have an intuitive sense for, and we've developed an intuitive sense for it. And then we said, okay, well, we can treat distributions of charges in this way. They're going to act and they're going to behave this way. Then we said, well, that's not really right because there's positive and negative charges and the world is not net charged, it's net neutral. So what we have to consider is the fact that individual atoms have these weird things called dipole moments. All of them have it. Some of them are more polarizable and some of them are less, right? So we found that, for example, lithium is highly polarizable, whereas hydrogen, not so much, right? Okay. And then we said, well, let's apply that to all of material. And we're going to talk about wood, or we're going to talk about glass in the context of how much do the atoms inside of that material move. And this is the conversation about dielectrics, right? So in practice, the things that we care about are things like how much work am I doing? What's the potential that I'm getting? What's the capacitance? So to tie up today's discussion, we're going to start with something that seems really unnecessary, something I don't care about, which is capacitance. But this is going to lead us to work and then to force. And then we're done with today. Okay. Is that okay? Questions before we get started? Yeah.
Is all the stuff like at the end of chapter 4?
Yes.
Okay.
Yeah. Yeah. Chapter 4 probably goes into a little bit more detail than I care about. You know, if you want to do this long term, materials like crystals, for example, are polarizable in different directions by different amounts because of the way that they're structured. And so in practice, you have to care about things that have polarizability tensors and nonlinear dielectrics, but that's not important for where we're going. What we're going to see here is that we have electrostatics and matter. Those fields, electric fields, create charge distributions that influence the original field. Okay, what do you think happens with magnetostatics and matter? Well, I'll give you a hint. They're going to create magnetic fields that resist the original B. And say, okay, those seem really unrelated. That's funny that they're sort of similar. And I'll show you how it is that we can see because of this interplay between B and E fields. So everything you've ever experienced in your life, except for that dropping, is due to electromagnetism, either in the form of electromagnetic materials with matter or through light. And so we'll understand some of the most fundamental ways of understanding the universe in this class. Cool. Cool. Okay. So generally speaking, we're going to be looking here at the example of how we, let's see, do I want to do this one? I have 3 different examples for a dielectric here. Let's do the capacitance per unit length in a coax, right? What? Okay, so this is a chapter 4 example. So we're gonna look at the capacitance per unit length. Call this A. Call this B. And let's imagine there's some permittivity in there. And we're gonna say that this thing has a charge plus of some charge per unit length. And then up here, we're going to say something along the lines of the capacitance is defined like that. Is that reasonable? If you're familiar with how we set the capacitance in a coaxial cable like this? Okay. The first thing that we want to know is to understand what the heck this is, right? So in order to do that, you want to get the potential in a region, you need the electric field, right? So in fact, we'll need the electric field, okay? And in the last couple of classes, we talked about something that wasn't just the electric field, we talked about the displacement field. And we said that the displacement field is written like this. Now, what does the displacement field mean again?
Polarization plus the electric field inside, or?
Yeah. So essentially what you're saying there is that it's the electric field plus the result of the electric field on the matter, right? We're going to utilize this idea though. And we're going to note here and in the homework that they're relatable very easily. Okay, where I see E, if you have a polarizable material, you can see D. All you need is epsilon. Right? Okay. So you can use Gauss's law here, just like you would if there was nothing in between these objects. And you're very familiar with Gauss's law now? Okay. We're going to say D dot dA is equal to Q, the free enclosed. So this is the free charge enclosed. And the area here is straightforward. So it's just going to be the area of the surface. What's the area of any surface inside of here? Not this way, but this way. No. Very good. All right. So that's going to be something like D times 2 pi SL. equals lambda L. And thankfully enough, we have L on both sides, so it's not going to depend on our capacitance per unit length, just on the capacitance, right? Smart construction. That's things. Capacitance per unit, sorry, charge per unit length times length would be charge. See that? Okay, so then we can say something along the lines of, well, I know what D is then. That's just lambda over 2 pi s in the s hat direction. Not reasonable? What you would have expected? Okay. Similarly, we could say that E, by this definition, here, is this divided by epsilon naught. 1 or 2 pi epsilon lambda over s in the s hat direction. Okay. Now what would we do if we wanted to get this thing here? Don't say that. We don't say that. What is it called? You're very close.
Yeah.
There's a real word for it that I like more than that. Integrate. So negative gradient would be negative times the gradient,
Yeah.
right?
Yeah.
There is no negative gradient. You might say inverse gradient, but that's still wrong because a gradient's a specific vector function.
Right.
So we're just doing the integral here. We want to be a little more precise. Okay? But you're absolutely right. It's the integral. Okay, what integral? Yeah, that's right. It's an S. What else? E.
On the bottom.
No, I saw E from Isabel.
Oh, okay.
What else? D. L. Why D L? What is the potential we're talking about here?
From the outside to the inside.
Yeah. So you're going from the outside to the inside, right? Going from say A to B. And intellectually, we understand the relationships here, right? So if I think about a force, I'm thinking about electric fields. If I think about an energy, I'm thinking about the potential. And we already know in kinematics that the force and the work are related through a line integral. How much force over a distance, right? From point A to point B, that is the work. Do we see the similarity here? It's in fact the same definition, just with the idea of charge replaced with the idea of mass. Okay. I'm not going to make you do the integral. I promise it's straightforward, but you can put this E that you found down here up here. Actually, I wonder if you could do this. Very good. What is it? Anyone else have it? You have it memorized? It's okay, I don't have it memorized either. So we just said, Melinda.
I didn't say anything.
It's the natural log. Okay.
That's the end.
Yeah, what is the unnatural log?
Is it like log of anything else?
Log base 10. Yeah. For some reason, even if that's the one that we have fingers for, that feels more natural, but for some reason E is the natural log. Humans are natural. Yeah. Okay, so now we have V, you have Q. So what's the capacitance in the dielectric? Is that okay? Can I do that? Maybe capacitance per unit length, because I just cheated. And I said, I don't want it, the full capacitance. This is maybe infinitely long. So all I did was I just switched this definition here. Maybe I'll get rid of this. Doesn't matter. It's positive. Okay, so I took the capacitance per unit length. Right? I have my lambda is gonna divide. Right? So this is equal to 2 pi epsilon.
Side natural one. Medial, right?
Correct? Okay. So that would be the positive. Okay. For negative, right? You do the same thing. Change the charge. Take away half the dielectric, you find out what C is. So the way you could think about this is if you had like a positive here, lambda positive, and lambda negative out here, right? Then you'd have some bound surface charge distributing through this. The E field is radial, right? You have that axial symmetry. Okay. If I look at this form here, you're noticing something very similar about the capacitance. I don't know if anyone memorized the capacitance of a coaxial cable. Okay, well, if you look it up in the notes, it's very similar, but it has an E naught here, right? Permittivity of free space. E has no curl, right? So it's independent of angle here. In this section, the E field is going to look like, should I use a different color? This doesn't matter. You can see that it's right. Right? We're okay with that? Okay. Is it clear how you would do that? Okay. I get rid of all of these additional examples. If we want more examples, we have more examples, but I don't want to. Okay. So let's talk a little bit about the energy in dielectrics. Okay. So we have a dielectric here. Maybe we want to think about it in terms of a normal capacitor with two flat pieces and you have some box in between. We could have that picture too, but we're going to use this framework to understand the work involved. We're going to assume that that's perfectly true. Okay, two plates, one on top of the other, stuff in between. Okay. What is the work for an E field? What? You remember? We didn't talk about it in this class.
Instead of like traditional force, it's an electromotive force.
That would be like in a circuit.
Yeah.
But just generally speaking.
Oh, okay, so the force. That's this.
Okay, yeah, say something like that. You might say something like, you might have seen this before. Sorry, that's it. Okay. Have you seen that before? No?
Yeah. Who's our machine?
It's on your sheet.
I think, yeah, so we really used it. Yeah, it was like.
Yeah, you may not have used it. The important part here is, I mean, if you wanted to, right, you could calculate the energy stored in a capacitor. Because now you know the E field in that location, and you can figure out how much work it would do to separate the system. Right? So let's say you want to take one charge and you want to move it. You have to find out how far you're moving it through that E field. Right? Okay. You also know for a charging capacitor, you have something like this. And this one's funny, right? It looks like it has some parallels. Because we have this C that looks a little bit like the mass in the system, and the V that looks like velocity, but it's not that. Right?
Don't think that.
Don't think that.
You can see.
It looks similar, but it's misleading. Right? The functional form here is because they are in fact related. So this thing here is the potential, right? CV squared doesn't even have close to the same units of velocity, right? Even though capacitance sometimes acts like that's where the build of charge is. So if I want to charge the capacitor, this is what it'll take. Okay. This piece here, oh, I didn't actually write it down. So let's write this as C dielectric, maybe. That way I don't have to spell it. That's how you spell vacuum. I'll assume that's right. This is, by the way, I don't know if I said this before. The ER here, does anyone know what the R is?
That's that material.
Close, yeah, it's the relative permittivity. I don't think that I said that earlier, I just wrote it down. And I was like, I don't even remember what this is, so I looked it up. Because there's this E naught, free space, E, that's the material itself, and then this is the relative one. Okay, so how do we write this E? Because this last piece here is equal to E naught, the relativity of free space. Oh, sorry, the permittivity of free space versus the relative permittivity. Okay, and that's for a specific material. That's the definition. Okay, so if I look at this, and I look at this, I might be tempted here to just be like, well, you know, I had this thing over here, which essentially says that D is equal to epsilon E. Right? They're related in a dielectric. So maybe I'll just use that. I got an E naught here and I got an E. Okay. So for a dielectric, I can rewrite this because I'll need a version of ER in here. If I have some dielectric in this piece here. This is dielectric. Like that. Okay. So then I can rewrite this as or let's use the epsilon naught and the epsilon ER in here. And that would be E. Is anything we know? Good. Okay, so this says that the energy inside a dielectric is the product of the displacement field and the original E field integrated times half. Is that reasonable? Kind of guessed it because I knew where I was going and the book knows where it's going, but this is correct. You can prove it if you do the actual integrations from first principles. I don't want to do that, I don't care. But this is a good enough technique, right? If you can relate things in a dielectric to their original field times some fractional form of E, right? This relationship here really helps you because it tells you how these different pieces relate, right? The displacement field is always the relative permittivity times the original field. Is that a question? No. All right. So let's think about, oh, I guess I should have done the spherical capacitor, not the coaxial gate. Should I do a different example really quickly?
You could.
I was gonna do the work for a spherical connector and I apparently didn't write it right. If you had a spherical capacitor. So it's not a line, it's just a sphere, one inside the other. Okay. Dielectric in here. Okay. From this one, we can still use Gauss's law because I've obviously chosen a spherically symmetric idea, right? So I would say something along the lines of D is equal to Q enclosed over two pi r squared. 2 pi r squared? 4 pi r squared. Just want to make sure. Okay, so this Gauss's law tells us that I have this nice geometry. I can relate D in this Y. I still have that factoid over there. That E is just D over epsilon. So I can combine those two. Q is 4 epsilon. Okay, so now I have D and I have Q, sorry, I have D and E, and then I can put them in here, no? What would that be? It's a big interval, so let's do it properly. You can do it in your head, though. That's the nice thing. Oh shit. Oh, why did you read it? That's right. Okay. So how do I write the work in this system? If I need an integral. Good, yep, that's one of them. It's the bounds in a spherical coordinate system. 0, 5, 5, one of them. Am I done? What? 0 pi? 0 to R. So in this case, let's assume that I have exactly the same thing that we had before, but I did it the example properly. And I didn't do the coaxial cable, I did the spherical one. Indeed, very good. Okay. Now what goes in the mumbo jumbo then? That's multiplying, sorry. I mean. Q squared?
Q squared.
Good.
I did have a question on the parallel plate capacitor. Where, like, how did you just randomly put the permittivity, the relative permittivity in there? Like, it wasn't in that side, and then you just put it.
So I said this would be for no dielectric,
Oh, okay.
right? And I said this is for a capacitor. And I just made this analogy. So this is a leap of logic that is unproven. One of the funnest things you get to say as you get older is you say, well, I don't want to show this, so I'm going to leave it as an exercise to the reader. Right? You're the reader, so you have to prove it to yourself. So this is not in the book. I don't want to prove it. I don't care. Right? 100 years old. But you can find that it's right. And this logic works well enough. This is the practice you can use by saying, well, the displacement field is related to the electric field just by the permittivity. And that's what we're trying to understand. That the permittivity of the material itself creates this displacement field, and then we can do almost all of the same physics that we've had before, just make a small tweak, right? And so we have this small tweak here. So you have Q squared, what else do you have? You say 16?
Yeah.
Why 16?
14.
Oh, yeah, it's good. Oh, yeah. Anything else?
Pi squared.
Pi squared, okay. Anything else?
Epsilon.
Epsilon.
Squared.
It's not squared.
Epsilon not squared. Why would it be not done?
Oh, wait,
It's epsilon squared.
Fight, well, which one is it? It's just epsilon.
I guess
It is on the board.
you could rewrite it as epsilon not times epsilon r.
Yeah, you could rewrite it if you wanted. And then
And part of the fourth.
part of the four. Anything else?
Square on the top.
R squared on the top, interesting. See what?
We already defined.
No,
Oh, the order back.
It's
That's
spherical.
what-
It's spherical. Or-
The order. Did it?
Yeah.
In the middle of the sign.
There's a sign. There's a sign in there.
Oh, yeah, there is a sign.
There is.
Oops.
E and Q, the one nothing's good out here. I don't think there's like.
Yeah, there.
I
What's
don't,
that?
I don't want there to
No.
be.
Yeah, there's no point.
There's multiple.
But so far, yeah, I just wanted to make sure there's space in case one put in there. Alright. Okay, is this doable? Yeah, it's super doable. That's why I wrote it before.
Thanks.
So what happens to the R's?
They can
Yeah, where do they go to?
R squared.
Can we integrate this?
Yeah.
Can you do it in your head? Like it's, write it down for yourself. You can do this in your head. I'm gonna take all your constants out. Q, I'm gonna claim as a constant. 32 pi squared epsilon. You say you can do it? We got it?
Yeah.
Is it 0?
Oh, yeah, but I think it's still, isn't it still a fraction? It's the exponents. Yeah.
So yeah, once you change it, yeah, you could.
Yeah, what is this always? 4 pi, don't calculate.
Don't do it.
Why? It's silly, right? Just memorize what the spherical integral is for this part when there's nothing that depends on it. It's 4 pi. Can you do that? Hope so.
Yeah.
What do you think?
Oh.
Just this piece.
Oh,
That's the integral of r to the minus 2 dr.
Negative. Or, yeah, negative, yeah.
Negative 1 over r, right? Yeah, or at the bounds you would have.
It would be after applying the negative sign, 1 over a minus 1 over b.
Not a big bada boom. Get rid of one of these, get rid of one of these. Right? That's straightforward. Go ahead there, right? You didn't get stuck there. Because it's Monday, right? It's not Monday. There you go. I was making sure everyone's awake. Okay, but let's have a look here at the important part. The total energy, okay, is going to be reduced because epsilon is going epsilon naught in a vacuum. So the work in a dielectric is going to be the work in a vacuum divided by the relative permittivity. What? Yeah. Yeah. This is another way of saying the same thing. But I want you to think a little bit on what we're talking about here. Okay. I have some dielectric material. I provide an electric charge to it, or sorry, an electric field to it. This is going to redistribute the charges. The capacitance is going to change. Oh, no, I wrote it. How does the capacitance change? What did I write? Okay. I deleted it. C for dielectric is related to what for C without a dielectric?
The relative permittivity. C in the way.
Okay. And maybe it's worth making sure that we understand how this number moves, the relative permittivity. Is this 10 to the negative 36? Is this 451? Is this negative A? What is the value of the relative permittivity? From 0 to 1 or from 1 and above, right? So here, the relative permittivity is 1 in a vacuum. Because what is this saying? Let's write one more thing. How do I write E epsilon naught? Oh god, that's too many circles. How do I write these three things together? Are they related? What? Where do I put it?
On the left side.
Here?
No, that side.
Okay. Is that right?
Yeah.
So the relative permittivity is 1. Then the permittivity in the material is the permittivity of free space. Reasonable. Okay. What about if the permittivity is less than 1? The relative permittivity, is that possible? No, because you can't be less than the permittivity of free space. Right, so this number is always 1 or greater. So maybe I should have said that way more clearly. 1 or larger. Sometimes you don't know what you've done. I apologize. First time teaching the class. Okay. So let's look at this one here. In a dielectric, how is the capacitance change? Goes up. Always goes up. That's weird. What about the work there? Goes down. I mean anything to anyone?
Like over time, it's easier.
to charge the capacitor.
Yeah, that's easier to charge a capacitor. You got a dielectric in it. Why is that? Let's look at the geometry again. Okay, here's the geometry. I want to charge this capacitor. So I have material inside of my sphere. So maybe I have my coaxial cable, or maybe I have this example here. Whatever one it doesn't have. You start with no charge. Yeah.
Oh, I was gonna, that has an idea on it.
Okay. What do you think?
Well, since we're talking about how it's the permeability or the heat of the R,
Mhm.
if it's higher, would that make it easier?
Yeah, but why?
Is it-
Physically, what's happening inside the material? Right, because I want to take this stuff, which is very opaque to me. I want to make sure that I can construct a mental model of what the atoms, electrons are all doing inside of the electric field. That makes it so that it's true. Why is it easier to charge a capacitor?
Maybe because there's already some amount of charge in the dielectric materials, there's already like, electrons and stuff like that inside of it. So
Mhm.
instead of like having to like push the energy like much faster, or with the E field, like there's already E field in that dielectric when it's being induced.
Yes, you induce the displacement field,
Yeah.
right? And that's going to create bound charge.
Mhm.
Right? So it makes it simple.
By simpler, you mean easier?
Yeah, it takes more energy. So if I multiply this on the other side, right? This is gonna be a number larger than 1. So the amount that it takes to charge the capacitor with nothing in between it is larger than stuff. in between.
And the WD, that's work of those.
No, sorry, let's say this properly.
For the dialect.
Is that okay?
For the dialect.
Yeah, so the work in a vacuum, the work with nothing inside the capacitor versus the work with dielectric. So in practice, I told you that every capacitor that we looked at has material inside of it. And now you see a second reason why you want that. Right? One, so the plates don't hit each other. Alright. And two, because the material in there, it makes it easier to charge. Increase the capacitance. Put a thing. Okay. All right. At least everyone. We're talking about force now. We're almost done. There's 2 pages away from freedom. Then we don't have to do electrostatics. Then we get to magnetostatics. Better. So, questions on this before we move on? Everyone's fine. I don't know what to delete. I want it all. All right, we don't want this. How do we define the force in a dielectric? Say I wanted to have this capacitor fully charged up. I got this dielectric and I want to push it. Yes, like that, push. What do you mean? It's impossible, right? How do I start the problem? Yeah. I have a dielectric inside of a charged capacitor. Now I want to push it. Just like Jasmine demonstrated, I want to push with your hand, push dielectric.
Like,
Only the dielectric. So the charged capacitor, it's like this. We're gonna look from the side, and here's the dielectric. And here's some point x equals 0. I want to push it. F in the direction of x. I spend 3 minutes talking to your neighbor about what the hell you would do to start this. Gotta wake those brains up.
What are we trying to do?
I want to push the dielectric.
Yeah.
How'd you do it?
Well, you can push it with your hand or you just like.
Yeah, I want to calculate the force. How much push do I have to do?
How much?
How much push? How much force?
Equation probably.
What does it mean? That's a very good question. Like, what is the relationship? Oh, we've talked about work, we've talked about D. Can you tell me what would you do right now to even begin to start a problem where I ask you to calculate how much force you need? I'm not asking you to solve it,
Yeah.
I'm saying what would you need to even think about it?
Yeah. So we either need is a most electric. Or a combination of another magnetic field. To get it to Earth, I don't think it's not. That's what I'm thinking. I mean, I guess you could. Say that.
I don't think
Yeah.
Force tensor.
A little bit of
Coulomb's
Coulomb's
law.
Is that your response?
Yes, you'll need Coulomb's law.
What's Coulomb's?
That's well, I guess force equals Q times E plus.
That is not Coulomb's.
I think something else.
Yeah, Coulomb's law is the 1/r squared force.
Okay, never mind.
Okay, that's why I was looking at you very quizzically.
Just kidding.
Because what you said is, it could be right for point charges.
Yeah.
QE, right? We do know that E for a point charge is that.
Yeah.
And so maybe there's confusion there because QE, when you're learning about point charges, is always shown that way.
Yeah.
But Coulomb's law is QQ over R
Yeah,
squared,
that's
right?
not what we want. We want the. Oh, is it one? No. No, it's,
What you got? You got Kobe.
I don't think it's.
I got what you got read.
We were wondering, are you talking about pushing like the actual capacity?
No, just the dielectric.
Just the-
Capacitor stays still. I push dielectric. So imagine the dielectric is made of linen. I put my shirt in the capacitor. Now I want to push my shirt through the capacitor to get it back out because I'm done with my experiment. You can't.
Physically push or.
Yes, I'm going to push it, but I need to calculate it first, obviously. Right? You can't just do something, you have to calculate it first. We want to understand how forces work. Are there any relationships we could use? I heard one.
Yeah. So there's a relationship between the electric field and the magnetic field.
Okay. There's no make.
I'm just kidding. There's a relationship with force in the magnet or electric field.
Uh-huh.
So a charge times E. We drop a charge into an electric field, we will experience a force.
Ah, okay, good. Right, that would work for point charges. But that's right. Okay, so this is useful, especially when dealing with point charges. Maybe not generally. Anything else we can use? What?
Maybe.
I don't have any torque in here, because I don't, a torque, right, if I did something like torque, I think I wrote it as N
Yeah.
equals
The dipole.
Q cross,
Oh, yeah.
sorry, P cross E,
Yeah.
or R cross F.
Yeah.
That's not really giving us what we want.
Yeah.
Isabel said, work is force distance.
Work is force times distance, huh, what an interesting idea, because we just talked about work.
That might.
Now, is this correct? You need a squiggle,
We do. And it's.
Right?
Is it negative?
so the inverse operation here is
Gradient. Just kidding, partial.
I mean, it's the gradient kind of, but
Yeah, but like.
we're gonna do it in one direction here because I've already written f of x on the board. Is this reasonable? No. Really unreasonable. How would you expect us to know that? That's from mechanics. Why would we ever use mechanics in a different class, right? Okay, these are the fundamental relationships between these properties. You always want to remember these. Doesn't matter whether we're doing particles accelerating, doesn't matter whether they're influenced by an electric field. This relationship between force and work is important. right? So sometimes, we saw this in 2500, you couldn't calculate the speed everywhere using the forces. So you calculated conservation of energy, and then you found the velocity, right? And then you have to like turn your brain back a lot to remember that. All right, reasonable? Sometimes it'll be easier to calculate the work, okay, from something like this, D times E, which is the potential displacement, or sorry, the displacement versus the electric field. Then it will be to simply calculate this everywhere. For point charge, right? So this would have to integrate this entire object. Reasonable or no? Useful to have both techniques? Yeah, I'm telling you that. So. Okay. All right. So we wrote that already. What's the work on a capacitor?
What is the word on the unit? Yeah.
Oh.
That one.
One half,
1/2 CV.
It's right there, right?
Yeah.
Okay, and with the dielectric in it, it's even easier. So we could say something along the lines of, okay. We're gonna make some assumptions here. In your book, they show the whole thing. I'm not gonna do it. Okay. Hold the voltage constant. Okay, then the capacitance will change as the dielectric moves. Right. You can say something along the lines of the total charge is the capacitance times the voltage. One goes up, the other goes down. So you might say something along the lines of, let's hold the total charge constant. Okay, and rewrite the work.
So it can be like factor out of CV.
What?
Is that what you mean? So-
You want to factor out a CV? No, I want to add Q in.
Oh, okay. Got it.
I want the total charge to
That's-
remain constant,
Okay.
right? So I want something along the lines of work is actually more closely related to something like this. No, you don't like it? Okay. So this is held constant in the capacitor because the capacitor is hooked up to a battery, right? So you might be able to say something along the lines of, if I write this better, I could write F is. Oops. I guarantee that I'll mess up these negative signs, but don't worry. Okay. Let's do the derivative here. How did I do that? The magic? No, not magic.
How do you know to do the C?
How did I know to do the C?
Yeah, we're like,
I think the version, so I can type, or derivative C, just like that.
it's like implicit.
So we're saying that Q doesn't depend on anything. We're gonna say that it's constant, right? So one of these is gonna have to change. So I'm making a choice right now. And I'm saying that I'm gonna let the capacitance change as I push the dielectric out of the material. Right? Because notice what happens is at the very beginning, the capacitance is larger due to the presence of the dielectric. When I start to remove the dielectric, as I push it, what happens to the capacitance? It will go down. So I already know in my head that the capacitance per unit length is an object that is changing. Right? As I push it out, it will go down to a vacuum. That's the choice that I make, right? So now I can see, okay, if I distribute this in here, this comes out. Q, no big deal. And then C to -1, from C to -2, that comes out. And then I do the channel.
Yeah.
Reasonable, right? You may not have guessed this. I'd have no expectation that you would get a homework problem and you would get that on the first try. But the goal here would be to understand if I have this relationship, right? I can move these things around so that I could just distribute these partials, and then I can say, well, this thing, I want to try to understand how does the capacitance change as a function of this, right? Is that knowable? Yeah. Is that knowable?
Yes.
Yeah, it's very knowable.
How did you get the partial C over partial X? Keep that part.
Okay, so the 1/2 Q comes out.
Uh-huh.
And then you have 1/C. What's the derivative of 1/C with respect to C? Or C squared. That's it.
Yeah.
But now I don't know what the derivative, right? Because remember, if I say something like this, derivative of 1/C, right? This is the same as saying the derivative of 1/C. Like that.
Yeah.
You ever seen that before? That notation? I just baked it right in. Because I don't know how this variable changes,
Oh,
right? That's built right in here. Okay. So what would have happened if we had held V constant? Okay, you would get something that was. You can make the other choice. Let's write it. So you get the same kind of thing. Or you want to understand how the capacitance changes for unit length. Right? Okay. Is there any way to understand how the capacitance might change for unit length? Is there any way to understand the capacitance at all? Yeah, good.
the charge over length.
Charge over length, right? Okay. Or charge over length? No, charge over. Not volume. Voltage, charge over voltage. So we said that right here, right? So we have this definition, right? And at every step, we could calculate the potential using all of this stuff. I'm gonna need to delete some. Write this all out. You have a distance x that you're gonna move. You're applying a force field. Some distance between them is d. It says some length L. In air, I would say that the electric field is sigma over epsilon naught. And in the dielectric, I would say what?
Over, yeah.
What did I say?
Oh, we're ready.
Okay, so I said, you have some surface charge in the dielectric. Okay. It's empty. You have some surface charge, call it Q. Put the dielectric in, what happens to the surface charge? What? Good hands, Isabel, what does that mean? It moves. The dielectric goes in. You have polarizable material. Bound charges appear at the surface of the dielectric, and they cancel out the free charges. So the bound charge or the free charge here is effectively reduced. So the combination of the two of them, bound and free, sum to less than the free charge from the capacitor. This is what's happening in the material, right? This mental model we're constructing. Okay, so bound charge or the effective bound charge at the edge of this capacitor is down. Okay. This is the new one. What happens to the potential? Well, in the air, it's just sigma or epsilon naught d. This is the distance between the capacitors in a parallel plate capacitor. Okay. In the dielectric, I get what? Same thing with these right here. So this thing. Reasonable or not? This is how our capacitor works, right? So this is our new surface charge. This is the permittivity material. And this is the distance away these plates are close together. Okay. We can write these things straightforward way. Sigma over epsilon naught is equal to epsilon naught over epsilon. Those are relatable, right? So what did I say here? The epsilon ER is the same. The bound charge is the same when the permittivity here is 1. Right? So how do I write this piece now? If I want to look at the total charge here, I could write this as the total charge as a function of distance. Let's say this whole thing is L, and our charge per unit length, for example, or charge per unit area here would be the product of sigma with the distance that we've covered, right? I could say something along the lines of Q. It's L sigma prime X. Minus X. As I'm moving the capacitor out. There's a small section, let's say, I'll write it like this. That's my dielectric. I've moved it some small distance, right? X, that's the small distance. Apply a force F. Here's the distance X. The total length. The total charge, the combination of this piece of charge where there's no dielectric, and this piece where the dielectric is. Yes? How did you get that equation? So this piece is where there's no dielectric. Right? That's what the sigma is. Times unit length. Right?
Yeah.
This is how much of that there is.
But I get that part, but like, how do you get the 15? Why Q equals L?
So this is the YQ equals L.
Yeah,
Oh, because this is a surface charge, right? So we're imagining, sorry, this is L on both sides. So there's some surface charge, right? Some parallel plate capacitor that's a square. Okay, so it's L times on both sides. I mean, I can divide by L in 2 seconds. Right, we can do charge per yield, I don't really care about that. But as I move this capacitor in or out. Right? Oh, I did this back. This one here, sigma times X is how much air is exposed. So as X becomes larger, as X goes all the way to L, then this one over here, L minus X becomes 0. Right? Whereas when it's the dielectric's fully in the object, then X is 0. And there's no free space. Is reasonable how I constructed this? Even though I did it wrong initially, yeah.
So the left side, does that focus on how much like air and free space is between the capacitor?
Yeah, so this is the air side.
Yeah.
And then this is the dielectric side.
Okay,
And not air, because air is the dielectric, it's the.
Okay.
Vacuum. We tend to think of it, air as a vacuum, but it's not. There you go, okay, hopefully it's not a vacuum, just breathe in. Question? Okay. So you can simplify this using this one down here, but sigma's everywhere. Sigma L is eta R minus 1 times X plus L. I think I have a sign wrong here. Let's do that less. That's right. So let's distribute this one first. So this thing becomes epsilon R sigma. So now sigma's everywhere and we can pull it out. L is everywhere and we can pull it out. You see that? So this is X plus L epsilon R minus X epsilon R. See that? Correct? Did I do it wrong? Trusting you. Okay, then we can rearrange a little bit more. Let's separate this one out. Let's grab the X's here. This is minus the susceptibility of the material. Oh, very confusingly, this large X with the little twiddle on the side is the susceptibility. Okay. So this means I could write, now that I have Q as a function of X, right here. The whole reason for doing this was so that I could write the capacitance as a function of X. I have the voltage. So I could write something like C, combining these all together. Oh, God, I don't have space. No, I wasn't supposed to do that. I could write C as Q over V. What? That mess. Quantity X, weird X, yeah.
plus M. Yeah. Over D.
What's the,
These sigma over epsilon. Yeah, that.
Remember, there's a lot of capacitance in this.
what?
Where do we want to know the capacitance, like after the dielectric has been removed or while it's still in there? Because why are we using epsilon dot?
We can change it out.
Okay, so we have the charge here,
Oh,
we have the potential here, or sorry, the potential as a function of distance. And I really want to write this in terms so that we can get rid of this sigma. Sigma I want to write as a function of distance. Top to bottom. Got it. That's the reason that it's true. Get rid of that one. And that's not like easier, but it's fine.
that on our final.
It's calculable.
Yeah.
It's just a bunch of numbers thrown together. Okay. So what was the technique here? What you're looking for is a way to put, these relationships that you have, Q, C, V. Can we put them in terms of the properties before and after a dielectric is applied? And trying to continue to go back to the original mental model that we have, which is that as I move something, it's going to change the original field. It's going to displace the field because the material itself is polarizable, right? I didn't actually assign a homework problem today. How long was the homework program? Able to do it all? I'm going to see that in 2 minutes. But longer or shorter? Raise your hand. Raise your hand for longer. Raise your hand for just right.
Yes, sir. I think.
Raise your hand for shorter. Okay. All right. So we'll try to do 3 problems. I didn't actually get to one today, but I'll assign it. It'll be something similar to this, talking about how to use work and forces in the material itself. We have exactly what, 2 minutes left. Any questions? Finished too early, yeah.
I was kind of confused how you got the L times sigma X. Like I get why there's 2 different ones, but I'm confused why you put that in thing.
Well, what is sigma?
It's the bound charge.
Yeah, but what is the units? Yeah, charge per area.
Yeah.
And area is length times length, right?
Okay, yeah.
So I'm just constructing with
I see.
broad strokes.
Yeah, I see it now.
That's how much charge is associated with the vacuum. How much charge is associated with the dielectric. Any questions? Okay, for Thursday's class, you'll be jumping into chapter 6. I'm hoping we'll just move through that about 2 weeks. We'll fly through the magnetostatics and matter. It's not that surprising. What you're going to see is that we add charges in, they start moving, they affect the field that created them. Magnets do the same thing, except there's no magnetic charge. You apply a magnetic field, all of these electric particles start moving, and then they create their own B fields. So far we've completely ignored B fields, and yet every moving charge, according to Maxwell's law, does what? Creates one. Okay, and we haven't even talked yet about how the hell this force is communicated. We'll talk about that. All right, questions? Anyone have a homework that they need to turn in?
I don't know, we